In this video, we're going to discuss multicollinearity. In an earlier video, we discussed perfect multicollinearity, and we noted that was a violation of one of the assumptions of the classical regression model. If there's an exact linear relationship among two or more of the independent variables, we have perfect multicollinearity, and in that case, model parameters cannot be estimated. Remember, the slope coefficients in a model are a measure of how the dependent variable changes when that specific independent variable changes, holding everything else constant. If we have an exact relationship among the independent variables, we're not able to measure any independent variation in the affected variables. The solution is based on the fact that perfect multicollinearity usually occurs when the model is not very well specified. It occurs when an identity exists among the independent variables that was not taken into account. The most common example of that is when you fall into the dummy variable trap, where you include a set of dummy variables that represent a set of mutually exclusive and collectively exhaustive outcomes, where when you add them all together, they add up to a column of ones, which would be perfectly collinear with the constant term. It also occurs if there's an identity that exists among the independent variables. For example, if you're dealing with national income accounts, we know that disposable income is defined to be the sum of consumption and savings. If you included consumption, savings, and disposable income all as independent variables in some equation, you'd have a perfect multicollinearity issue. When we talk about multicollinearity in practice, though, it's generally not perfect multicollinearity. What you're more likely to contend with in practice is the situation where you have near perfect multicollinearity, which is what we normally refer to when we use the term multicollinearity. And that occurs when there's an approximate linear relationship among some or all of the independent variables. So we don't have an exact relationship among them, but we have a relationship where there's very little independent variation in one or more of the variables separate from some of the other variables. Perfect multicollinearity normally results from model misspecification, where you didn't consider a linear dependency among your independent variables. Near perfect multicollinearity is a much more common phenomenon. The consequence of multicollinearity is that because some of your variables are moving together, you're not going to be able to get very precise parameter estimates. One of the consequences of multicollinearity is that because you have very little independent variation in some of your variables, your parameter estimates are going to be relatively unstable. That shows up in relatively high standard errors for the estimated coefficients on the affected variables, and therefore, you'll see relatively low t-ratios on the variables that are affected, assuming that there really is a relationship between the dependent variable and the independent variables. The symptoms of multicollinearity include high standard errors and therefore low t-ratios on some or all of the independent variables, but that's accompanied by a relatively high R-squared. When multicollinearity is present, you'll often find that as a group, the variables are relatively important in explaining variation in your dependent variable, but you're not able to get very precise measurements of the effects of individual variables. You'll also generally see in that case that estimates are very sensitive to changes in data. So if you add or delete an observation, you often will see, because of the instability in the parameter estimates, surprising signs or surprising magnitudes, where you might see extremely large coefficients on some variables and extremely small and negative coefficients on others. When multicollinearity is present, one of the symptoms, and also a rough test for this, is that the variables that are affected by this will, as a group, be statistically significant, but you often would experience insignificant t-tests for the individual variables. Another symptom is that you find very high correlations between two or more of the affected variables. The symptoms actually suggest some ways in which we could diagnose an issue with multicollinearity. A simple way of doing that is, if it's caused by high correlations among the variables, you could look at the pairwise correlations among the independent variables. And if you find extremely high correlations between pairs of your independent variables, that's likely to be a sign that you may have some multicollinearity issues. You can also use f-tests to examine the joint significance of sets of variables that are individually insignificant. And again, if you find that as a group they're significant, but individually they're insignificant, that's generally the result of multicollinearity. The other thing you can do, and this is a somewhat more formal test for this, is that you could estimate what are called auxiliary regression equations. And the format they take is that if you have k independent variables, you run k regressions, where each of the independent variables is regressed on the other k-1 independent variables. And this serves as a direct test for the degree of linear relationships among your independent variables. A simple rule of thumb is that you should suspect multicollinearity if the r-squared is larger for some of these auxiliary regressions than the r-squared in the underlying equation that you're estimating. In general, a high value of r-squared for one or more of these equations is telling you that there's a high degree of linear association among your independent variables. An equivalent approach is you can take those auxiliary regressions and compute the variance inflation factors, which are defined to be 1 over 1 minus r squared sub j, where r squared sub j is a value of r squared in the jth auxiliary regression. A relatively high value of the variance inflation factor suggests that you may very well have a multicollinearity problem. The particular threshold is not very well defined because this is not a formal test, and here, as a rough rule of thumb, a variance inflation factor greater than 30 would often be seen as representing a severe multicollinearity problem. To remedy a problem of multicollinearity, one simple solution is acquire more data. The basic problem is you don't have enough independent variation in the individual independent variables to get reliable estimates of their separate effects. Acquiring more data could help alleviate that problem, if that's feasible. If you're dealing with time series, you may not want to wait to acquire more data. If the same degree of multicollinearity occurs with the new observations, it may not make very much difference. One thing you could try doing is dropping variables from the model, and many people do this. But most econometricians would argue that this is an extremely bad practice, because if the true model includes all of your variables, dropping variables that are important in the equation generates omitted variable bias, which will result in bias and inconsistent results for all of your model parameters. You might be able to come up with a reformulation of the model where the transformed variables may not be as highly correlated. And one approach with time series data that people have sometimes used is to compute first differences. Instead of having a regression of y versus a series of x variables, you reformulate the model where the change in y is a function of the changes in the x variables. But if you don't have autocorrelation originally, when you compute first differences, it may very well result in autocorrelated residuals. And it also would result in a loss of sample information because when you take differences, if you have 50 observations, there's only going to be 49 changes in those variables because there is no change in the variable observed for the first observation. But more generally, I think, in evaluating the issue of multicollinearity, we could just ask the question, is multicollinearity really a problem? If multicollinearity is present and all the assumptions of the classical regression model are satisfied, your parameter estimates are still unbiased, consistent, and efficient in that case. And the basic problem is you don't have enough information to come up with reliable estimates. Eliminating variables to solve multicollinearity problems generates estimators that are biased, inconsistent, and inefficient. And given that choice, most econometricians would encourage you, if you find evidence of multicollinearity, the best practice is probably simply to report that and provide any evidence and know that that can lead to parameter instability and may be the cause of the low t ratios that you may experience in your model. But in general, multicollinearity really is equivalent to a problem of small sample size. And the best approach simply is just to report it and then move on.